we will discuss Ohm's law. So let's first look at a hydraulic circuit. So in a hydraulic circuit, we have a pump, then we have a load, and then we have, of course, a reservoir, which is zero pressure fluid, right? So the pump pumps it up, goes through the turbine or some other kind of load, and whatever pressure is generated across the pump is basically used up in driving the load, right? Now we know that if the pump produces larger pressure, then there will be more flow, and if there is a larger load over here, then the flow would be less, right? So we know there is a sort of a relationship between the pressure applied as well as the load that exists in the hydraulic circuit, and both of them give you some flow. It's a similar situation with an electrical circuit where you have a battery or a cell and you have a load. So load is being shown as a resistance R over here, and we have some voltage that exists across this. So if we increase the voltage difference between the positive terminal and the negative terminal of the battery or the primary cell, then we know that we will have a larger current. And if we increase the resistance, then there will be a lower current, or if we decrease the resistance, there will be a larger current. So it looks like as if by changing the voltage and resistance, we can change what the current would be. And the relationship that governs that behavior is defined as the Ohm's law, which is voltage equal to current times resistance. So if you plot voltage against current, essentially you have a straight line where the slope of this line gives you the resistance value, right? So if this is the cause and this is the effect, then you can see that increasing the voltage will increase the current, and decreasing the resistance will also increase the current for you. So you could also say that current over here is a dependent quantity because it depends on what the voltage value is and what the resistance is. So if we do a simple example, let's say I have a 9-volt battery. Okay, I have a 9-volt battery and it's connected across a 100 ohm resistor. All right, and my question is, what is the flow of the current? Then I can use my Ohm's law. Okay, so we have the voltage dropped across the 100 ohm resistor is 9 volt. And why is that 9 volt? Because this point over here is at the same voltage value at this point as this point as this point, and so on, right? So let's say this point is A and this point is B over here. So the point A and B are basically the two extreme points of the resistor, 100 ohm. In reality, of course, there will be a voltage drop across the wire, but we're neglecting that. So the voltage drop across 100 ohm resistor is 9 volt, which is VA minus VB. Notice that because the current is flowing this direction, the voltage at A should be more than voltage at B, and that is equal to I times the resistance is 100 ohm. So I we get is 9 over 100 ampere. So that's what, 0.09 ampere, or we could say this is 9 milliampere, right? Sorry, that would be 90 milliampere, not 9 ampere, not 9 milliampere. So Ohm's law can be applied to different kinds of circuits. So we'll discuss two kinds of circuits over here. One is the series circuit. So as the name implies, in a series circuit, you have the resistances or the loads basically applied in series. So for example, you could have 3 resistors, let's call it R1, R2, and R3, connected in series end to end, and there is a single battery. Let's say this is, applying a voltage V, could be, 6 volt, 9 volt, 12 volt, doesn't really matter. But we know what this, voltage difference is, as well as we know what these resistance values are. Okay, now the question is, what is the current in the circuit if you have 3 resistors added together in series? What are the voltage drop across each resistor? So can we answer those questions? And yes, we can answer those questions. All we need is the Ohm's law, which says that the voltage drop across resistor is equal to I times R. So voltage drop, so delta V is equal to I times R, and that's what we will apply repeatedly for each of these resistors. So the first thing to notice is that since this is the positive terminal and this is the negative terminal, the current I is going to flow in this direction. Remember, the flow of the direction of the current is always assumed to be the opposite of the flow of the electrons, and we know electrons go in the opposite direction, right? So the electrons are actually flowing this way, while the current is assumed to be moving in the opposite direction. Okay, so we know that there is current I flowing through these resistors, and it's the same current that has to flow through each of these resistors. And that's because these three resistors are connected in series, that it can't be any different from each other. Okay, so it's the same current flowing through each of those three resistors, which means that we can apply Ohm's law for each of those three resistors. So let's say this point is A, this point is B, this point is C, and this point is D. Okay, so let's focus on R1. Okay, let's focus on R1. So what can we say about the voltage drop across R1? The voltage drop across R1 is given as VA minus VB. And clearly, because current is moving from A to B, VA should be more than VB. So this is a positive quantity, should be equal to the current flowing through the resistor R1 times R1, right? What can we say for R2? For R2, we can say voltage drop across R2 is equal to current times R2, right? So there is a voltage drop that's happening across each of these resistors. And what is that voltage drop? It's these numbers over here, right? For R3, we can write VC minus VD equal to I times R3, right? Now we can add all these three equations together and see what we get. So these two cancel and we get VA minus VD equal to I times R1 plus R2 plus R3. Okay, now what's VA minus VD? So VA is this point, VA is the voltage at this point, and VD is the voltage at this point. But point A is directly connected to the positive terminal of the battery, and point D is directly connected to the negative terminal, right? Assuming that there is no voltage drop in the wire in these sections, there's no voltage drop, then VA is the voltage at the positive terminal of the battery, and VD is the voltage drop across at the negative terminal of the battery, right? So VA minus VD is basically nothing but the voltage difference in the battery. So the battery is rated for 9 volt, then VA minus VD would be equal to 9 volt. So what we have here is nothing but the voltage of the battery equal to I times R1 plus R2 plus R3. So we can compute what I would be from that. So that would be V over R1 plus R2 plus R3. So let's do an example. Let's say the values of each of those three resistors is equal to 100 ohm, okay? And the voltage across the battery is given as 9 volt. Then what's the current? Current flowing through the circuit is equal to V over R1 plus R2 plus R3, and that's 9 divided by 300 ohm. So that would be what? 3 divided by 100, so that's 0.03 amp, which is equal to 30 milliamp. So that's the current flowing through the circuit. Now if you compare this with the previous example, you can see that the current has been divided by a factor of 3, because now you have 3 resistors in series. So you can lower the current in a circuit by employing multiple resistors in series. Now let's answer the question of the voltage drop across each of the resistors. Okay, so what is the voltage drop across R1? So voltage drop across R1 is VA minus VB equal to current times R1. Current we have just computed is 30 milliamps, so that's 13 to 10 power minus 3, and R1 is equal to 100, so 100 ohm, so that would be equal to what? So this would be 3 volt, right? That'll be 3 volt for you. And similarly between B and C, which is I times R2, would be same because these numbers are same, so that's 3 volt, and between C and D is also 3 volt. Right? So there is a 3 volt of voltage dropped across each of these 3 resistors. And what is the voltage at the source? The voltage at the source is 9 volt, right? That's the 9 volt. That's the battery voltage. So that's 9 volt. So the 9 volt that is coming from the source has been now equally divided across the 3 resistors. And the reason it has been equally divided is because the resistance value of each of the 3 resistors is equal. Okay, now if the 3 resistance values were not equal, then you will have unequal voltage drop across each resistor. So for example, if let's say R1 was more than R2, okay, if R1 was more than R2, then since the current is same, there will be larger voltage drop across R1 compared to R2, right? At this point, you can probably answer this question as to how different appliances in a household are connected together. You know, let's say your refrigerator, your dryer, your washer, your blender, your fan, are they connected in series? Well, you can probably tell the answer now that they would not be connected in series, because if let's say one of the loads is removed, then you essentially have an open circuit, right? So that means that no current can flow through this, and that means all of your appliances would stop working, right? If you remove one of the loads from the circuit, and then that means it creates an open circuit and nothing no current can flow through that. That means that would be a bad scenario. You can't have your refrigerator working unless your dryer is on, unless your blender is on, or unless your fan is on, right? So this is an example of a series circuit. Now, another terminology that is associated with the series circuit is that something called effective resistance, called effective or equivalent. It's also called equivalent resistance. So effective resistance or equivalent resistance is the resistance as seen by a certain source or between the 2 points. So for example, if let's say I wanted to replace this entire circuit with a single voltage source, the original voltage source, and a single resistor. Okay, so let's say this is what I wanted to do. So I will replace all the resistors, all the load with R effective with the same voltage source. Then the question is, what is that R effective? Okay, so in this case, you can probably tell the answer to that question, readily, because if you look at this equation, this tells you basically what your effective resistance would be. So for this circuit, what is the Ohm's law? What does the Ohm's law say? It says V equal to the current times the effective resistance. Right? So if we compare this equation with this equation, if you compare these two, you can clearly see that R effective is equal to R1 plus R2 plus R3. So in other words, we are saying that as to what is the total resistance value as seen by your voltage source. Now, at times, you may also be asked for the effective resistance between two other points. That's also a possibility, although that's not going to happen in this example, but it could happen where you're asked for resistance seen by two different points. Okay, so that's the effective resistance for this particular circuit. Now let's talk about parallel circuits. Okay, so parallel circuits. So what are parallel circuits? So in a parallel circuit, your resistances are connected together in parallel. So we have three resistors here, let's say R1, R2, and R3, and we have a single voltage source, okay, that connects across the three resistors. Now this configuration is different from what you saw before. In serial configuration, resistors were connected end to end, so they were connected end to end. Here they are not connected end to end. Here you have resistors that are connected together, they're tied together at the ends, right? So all these points are connected together, they're tied together. So which means that at all of these points, A, B, C, the voltage is essentially same, right? Assuming that there is no voltage drop, voltage at A, B, C is same. Let's say this is D, E, F, then the voltage at D, voltage at E, and voltage at F will be same because they are basically the same points, right? So this could also be drawn, like this. So you have three resistors, and now I've sort of curved them together, and they're all connected at the same point at the ends, right? This is called a parallel configuration. So in a parallel configuration, the voltage drop across each of these three resistors is same. Okay, so that's how we define the parallel configuration. If the voltage drop is same across two resistors, then they're clearly in parallel configuration. So let's say, this is point A, this is point B, this is point C, this is D, E, and F, right? So we've seen that VA should be equal to VB, should be equal to VC, and should also be equal to the voltage at the positive terminal of the battery, right? And VD, let's call this as V1, and VD, VE, and VF are same, and let's say that voltage is V2, which is the voltage at this point, right? So this is the voltage at positive terminal V1, here is V2, and V1 minus V2 is nothing but the voltage of the battery, okay? All right, now once we know that, then we can apply Ohm's law for each of these resistors. So we have V1 minus V2 is equal to I times R1. Now the current emanates from the source I over here, goes this way, and then it could get divided between these two sections. So let's say this is I1, and then again it gets divided between these two sections. Let's say this is I2, and then over here is I3. So the current flowing through let me flip this, because I want this to be I1 actually, and this to be I2. That's okay, I2, and then the third one, and see this being I1, I will call it I3, okay, just to match it with the subscript for the registers. So that's good. So we get that, and then we have also V1 minus V2 equal to I2 times R2, and V1 minus V2 equal to I3 times R3, and they're all equal to the voltage from the battery, right? So V is common to all of them. So from this we can write I1 equal to V over R1. From this I can write I2 equal to V over R2. And from this I can write I3 equal to V over R3. So if we wanted to know what the total current is, of course the total current coming from the source would be I1 plus I2 plus I3. Why is that? Because you have I3 going this way, and you have I2 over here, I1 over here. That means here it should be I1 plus I2 in this segment, and that means here it should be I1 plus I2 plus I3, right? Okay, so that's the total current going through them. So if I add 1, 2, 3, these three equations, what do I get? We get I1 plus I2 plus I3, that is equal to the total current from the source equal to V times 1 over R1 plus 1 over R2 plus 1 over I3. Right? So the question was, what is the current flowing in the circuit emanating from the source or the battery? We could find that. So let's do an example. So let's say the V is equal to 9 volt, okay? And my resistances are each of them being same, being 100 ohm, okay? Then what is I equal to? I is equal to 9 times 1 over 100 plus 1 over 100 plus 1 over 100. So that gives you what? 9 times 3 over 100. So that's 27 over 100 ampere. So that's basically 270, milliamp for you. That's the current. So what is the current through individual branches? So let's say the current going through R1, what is that equal to? I1 is equal to V over R1. V is 9, R1 is 100. So that's 0.09 ampere, which is 90 milliamp, right? Similarly, I2 would also come out to be 90 milliamp, and I3 would be equal to 90 milliamp. And you can see that if you add each of these three currents, 90 milliamps times 3, you get 270 milliamp. That's the current emanating from the battery, right? So from the battery, you had 270 milliamp of current starting, and then it gets divided equally in the three segments into 90 milliamps each. So you can compare this circuit with the previous circuit. We have the same resistors of the same resistance value of 100 ohm. Previously the current in the circuit was only 30 milliamp, but if you take those three resistors in parallel and combine them as shown over here, then the current actually is increased. That means effective resistance should be much lower compared to for the series circuit in this case. Now let's talk about the voltage drop across each of these three resistors. So the voltage drop is defined as I times R, right? So for the voltage drop across, let's say the first resistor would be I1 times R1, and I1 is 90 milliamp, so that's 19 to 10 power minus 3 amp, times the resistance is 100, so that would be what? 9 volt, right? Similarly, V2 is I2 R2, and since the numbers are same, that will be 9 volt, and similarly for V3 also is 9 volt. So the voltage drop across each of these three resistors is 9 volt, and of course that should be true because that's the premise we started with, right? We said that the voltage drop across each of these three resistors is same as the voltage drop across the battery source. Okay, now the last question to answer is, what is the effective resistance for this circuit? So effective resistance as seen by the source of this circuit, which is the battery, right? So if I have to replace this with one single circuit where I have my battery intact, that's 9 volts, and then I want to replace all the resistors that are here in parallel with one resistor of effective resistance, what would that be? So for this, the equation is V equal to the current times R effective, right? So if you compare this equation with this that we obtained, then you can readily see what the effective resistance would be, right? So we have I equal to V over R effective from this. So if you compare this one with this one, let's say this is 1, this is 2, you can see that 1 over R effective should be equal to what's over here, right? That's what we should have. So let's write that. So 1 over R effective is equal to 1 over R1 plus 1 over R2 plus 1 over R3, right? That's what we have by comparison. So if I want to find my effective resistance, all I have to do is take the inverse of each of these, and then I can compute my effective resistance. So imagine what would happen if, let's say, you had an infinite number of these resistors in parallel, right? So let's say I have one, and I have another one, I have another one, and I continue this. Okay, I have infinite numbers. So this is R, this is R, this is R, and this is R, and I'm looking for effective resistance of infinite number of these resistors, what would that be? So you can see that 1 over R effective should be equal to 1 over R1, let's say simply 1 over R plus 1 over R, continue. If it continues up to n times, this would be n over R, right? So 1 over R effective would be n over R, which means R effective would be equal to R divided by n. Yes? So if n in the limit, if the n goes to infinity, what happens to R effective? R effective actually becomes 0. So if you have infinite number of resistors acting in parallel, then the effective resistance is 0. That may seem a little bit counterintuitive or even contradictory, that you have infinite number of resistors and the effective resistance is actually close to 0. But that happens only because you have put them in this special, parallel circuit configuration. Okay.